Hi, good morning. My name is Neil and I'm a postdoc researcher at NERSC. I work on making molecular dynamics simulations more efficient to make them run better on the upcoming enterprise class high performance computing facilities. My primary area of interest is to work on the next generation MD potentials which use hybrid C++ Python based molecular dynamics framework. This brings us to a good question. So what exactly are molecular dynamics simulations? Well, molecular dynamics is a powerful tool to understand the interactions of atoms and molecules. It has applications in material science, biomolecule research, aerospace engineering, ionic liquids, and many more. As an example, what I've shown here in the center, the picture in the center is a molecular dynamics simulations of the spike protein found on the COVID-19 virus. And in this particular simulations, the authors had researched on how the spike protein interacts with the cell surfaces so that you can understand the scope of the power of molecular dynamics. So before we move on with the talk, I just want to give a brief summary about the terminology used for MD or molecular dynamics simulations. At its simplest terms, molecular dynamic interactions can be broken down into kinetic and potential energy terms. Well, as the name suggests, the kinetic energy terms are just that. They're calculated from the mass and the velocity of the atoms that are being simulated in the system. The potential energy term is a bit tricky to calculate. The potential energy term finds its contributions from the covalent bonds, which are the bond stretching, the energy that's used to stretch those bonds, the covalent angle interactions, and the dihedral terms, along with the non-bonded or the pairwise interactions, which are these terms which are called van der Waals forces or the Coulomb interactions. And the picture, the GIF that's shown here is a model of the energy that varies as the atoms move relative to each other. So we don't model these at random. They are governed by an equation. The equation in this particular case, as we can see from this equation here, is the Leonard-Jones potential. It's the simplest potential out there. So in summary, potential energy interactions are governed by an equation, or they may be governed by a series of equations, and these are now known as MD potentials or molecular dynamics potentials. So why do we really care about these MD potentials and why do we really need an efficient usage? Well, just to give you a brief idea, this pie chart shows the total workload of NERSC, which is where I work. And so you can see that the n-body simulations form a not insignificant part of the whole chunk. So if we make these more efficient, we'll be getting a better return on our computational investment. So LAMMPS, which is one of the most popular molecular dynamics toolkit, was developed under the auspices of Department of Energy, and it's been a multi-lab collaboration. In fact, it has been a beneficiary of the Exascale computing project under the project name of Exalt. So what's in it for the users? Well, efficiency matters. You have you can use less resources to get maximum amount of science done. You can now select better compute resources. For example, if you want to determine whether to use GPUs versus CPUs. And there's also something in it for the developers of the MD potential. With the methods that we'll discuss today, you can show performance portability, which is independent of the problem size and tailored specifically for the architecture on which you are targeting these applications. There's also a better compiler design feedback based on the methods that we'll learn today. There's a good back and forth between the compiler designers and the MD potential designers, as we'll see in this talk. And the necessity to have these compilers and the feedback between multiple design teams is that we just need to look at the upcoming enterprise class Exascale machines. And as you can see, each of them have a multiple systems of host and device, where the host is the CPU, the device is the GPU. And what we can see is on each of these machines, we have multiple vendors supplying multiple parts of it. In fact, if for this work, I have used Cori, which has two different kinds of CPUs on which you can run simulations, which is the Intel's Knights Landing and the Intel Haswell, along with a GPU, which is the NVIDIA V100. So in this talk, I'll be presenting you results on determining what was the best potential for any simulation on these three GPU architectures. And before we get to the results section, I would like to run you through most of the commonly used MD potentials that I have used in this analysis. And starting off with the simplest one, which is the Lennard-Jones potential, which is what we saw a couple of slides ago. It's just governed by a very simple equation. This is known as a 12-6 equation, where the parameters are just a power of 12 and 6. A further development of which, by adding a couple of dampening terms and additional terms to it, we come to the FENE potential and the charm potential. The FENE potential just has an additional term, which is this added interaction term. And for the charm potential, you have the dampening term. So this is not really a gain in the sophistication of the potential. It's just a couple of added terms to make it more accurate. Then we go on to another level of sophistication, where the potential now starts distributing forces in terms of normal and tangential forces, and this is what the granular Hookean model that we have. There was in 1980s, there was a huge jump in the accuracy of this potential, and now we start incorporating multi-body potentials, which take into account more than 2-body or 3-body interactions, and these are the Stillinger-Webb potential and the Tursoff potential. The Tursoff potential being extremely popular in usage today. Then the last final class of potential, namely the embedded atom model, the EAM, the REX, and the SNAP potential. Now we approach the accuracy found on the quantum chemistry simulations by incorporating some of the electron density and the bond order terms and the bispectrum coefficients in case of SNAP to bring the accuracy of MD simulations as close to quantum chemistry as possible. And these are the most sophisticated state-of-the-art potentials that we have. In fact, SNAP was a big part of the project on which I'm working on. And to give you a conventional idea on how these potentials compare, a good metric to go by conventionally was the number of time steps that are possible per second using each of these potentials. And as you can see, Lennard-Jones being simplest really gives you 470 time steps per second compared to the current state of the art, which is SNAP, which is just 31.018. However, I should warn you that the relative number comparison does not really give you a good idea on what potential is really the best. Sure, granted, a simple question might be, is it necessary to take this big of a hit just for accuracy? And the answer might surprise you, because it's not just that we need to compare potentials on the basis of purely runtime and accuracy. Now we also have a third thing, more important, which is how efficiently are these potentials using the compute resources we are throwing at them. There are multiple steps that potential developers have taken into account. Namely, there has been a push for parallelization strategies, where you have now paradigms such as COCOS and OpenMP, where we try to parallelize the code. And in this example, we can see that when you take just the REX potential, you get twice the number of time steps per second just by using the OpenMP version of it. However, which of these parallelization strategies fits best to the next generation of GPUs can also be determined based on the analysis. And for this analysis, roofline method is one of the candidates that we use to figure out how efficiently we are using the compute resources. And so the basis of roofline analysis is pretty simple. You have two roofs. One, which is this slanting roof. It's the measure of what is the maximum speed with which you can transfer data between the compute part of between the memory part of your machine and the compute regions of the machine. And this is a hardware bind, meaning that no data can travel faster than the computational bandwidth or the memory bandwidth of your machine. And the horizontal roof here is the peak compute throughput, meaning that what is the maximum number of operations you can perform on that given architecture. And so where these two roofs meet, if we draw an imaginary line, this forms the elbow line. Everything to the left of the elbow line, if your kernel lies in this region, it now becomes memory bound, meaning that your performance is now bound by the memory or the memory bandwidth of that architecture. Whereas if your kernel lies somewhere here, you are now compute bound, meaning that you are bound by the theoretical maximum available speed of that machine. If your kernel though does not lie between these two regions, you lie somewhere here, it shows that you have a good opportunity to improve your code, meaning that these kernels now show the maximum potential for, pun intended, for greater optimizations. And so when we compare, before we compare, we need to understand the memory layout in a very simple term. And so on majority of the compute architectures that we use currently, we have the high bandwidth memory, which is pretty cheap, and it stores a lot of memory. However, the connection between the DRAM memory and the memory parts or the cache levels of the CPU or the GPU generally form a major bottleneck in the performance of the code. And then you have either L3, L2, and L1, or just L2 and L1 cache before the data goes to the compute units or the cores of the machine. So this is important because moving forward, when I'll show you the results of the roofline plot, there will be 3 lines, each of them representing the bandwidth limits of DRAM, L2, and L1 cache. And so if we look at the DRAM roofline, meaning that this data was measured on the DRAM data movement to the DRAM level of the memory, we can see that the DRAM roofline of Lennard-Jones potential has multiple constitutive parts. And the most compute intensive are shown in red and the moderate ones are shown in yellow, whereas the low intensity kernels are shown in green. For the purpose of this talk, we need the cumulative performance of the Lennard-Jones potential, which is shown here. And so when you look at the hierarchical roofline measured at the L1 level of cache, L1 being the closest to the compute regions, so moving forward, we will look at data comparison at just the L1 level. This is because the L1 level is closest to the compute regions, and so all data has to move through L1 regions. One thing to note is that ideally we want our kernels to be upwards and rightwards. And the reason being, the next generation GPUs or the CPUs that are being developed, the amount of compute throughput, the Moore's law that's followed normally shows a big increase in the computational throughput. However, the bandwidth does not increase at that rapid pace. And so ideally, to future-proof our potentials or any algorithm, we need to have a kernel sitting upwards and rightwards. With that being said, let's look at the roofline analysis of the molecular dynamics potentials that are used in labs on Intel's Haswell, which is a CPU. And now immediately straight, you can see that all these kernels are tightly clustered in a very tiny region. And the reasoning being, most of the parts that are used for molecular dynamics, let's say for moving the atoms, for calculating the temperature, the pressure, etc., remain the same across any of the potentials that are used in this work. And in order to understand the differences, we need to zoom into that region. And we can see that this is the spread between the different potentials that we have. Now, if you recollect, the Lennard-Jones chain and the chain, which is the FENE potential, and the charm potential, which is the Rhodo or the Rhodo spin model, were pretty much similar. But if you look at the roofline model, the Lennard-Jones term is here somewhere. Even though the chain and the Rhodo spin model were much more complicated, if you look at the parallelized version, meaning that the COCOS versions, they show higher arithmetic intensity. Now, arithmetic intensity is how many operations were performed for every byte of data that was moved across the L1 cache in this particular instance. And we want this number to be as high as possible because, of course, we want the kernel to be as much rightwards as possible, which represents that more floating point operations were performed for less amount of data that's moved. So even though in terms of time steps per second, both the chain and the Rhodo simulations were slower than the Lennard-Jones potential, if the COCOS models were used for these two potentials, we would be making more efficient use of our compute resource. And this is the point I want to get across in this work. If you look at the state-of-the-art potentials, which is the EAM, REX, and the SNAP being the latest one, we see that their performance, which is the gigaflops per second, as well as the arithmetic intensity, is much better than some of these older potentials. And this shows, this is a testament to the improvement that has gone into making these potentials performance portable. Now, looking at what happens when you incorrectly use any given compute resource. And so this is the Intel's night landing CPU, which has a many number of threads, meaning that it shows greater ability to run codes in parallel. However, for this work, we restrict it to a single thread. And for COCOs, we restrict it to 16 threads, which is far lesser than the available resources on this CPU. And we find that, again, the arithmetic intensity is pretty much the same as compared to the Haswell version. And that's because for any given number of data, the same number of operations are being performed. And so obviously, you have the same arithmetic intensity. However, the performance is a lot lower. This is because no two cores are the same. The cores on Intel's Knights Landing is slower than the cores on Haswell, because there are many number of cores on Intel's Knights Landing. And so this represents an incorrect usage of this machine's resource. And as you can see, even then, the analysis that we obtained from our previous slide holds true even for this, meaning that a parallelized version obviously would have a higher arithmetic intensity. One thing to note is that if you look at the previous result on Intel's Haswell CPU, we find that our performance was bottlenecked by the L2 cache, whereas in case of Knights Landing, our performance is now bottlenecked by the DRAM memory, meaning that there is a bigger memory bandwidth between the big memory, the DRAM memory, and the Intel's Haswell compute architecture. If we look at the GPUs, we find that we have rooflines which are now bound purely by the DRAM, and they are extremely close to the DRAM, so we can certainly say that they are memory bound, which is not a great thing. However, it's not bad. Now we are restricted by the absolute memory bandwidth of the machine, and so we can optimize to have a higher arithmetic intensity and not worrying about utilizing the compute resources accurately. So there is still a room for growth, but we are much better compared to our performance on the CPUs. One thing to note is that if you look at the snap potential, it lies exactly on this line, meaning that it's on the border of memory bound and compute bound, which shows good utilization of resource. If you measure the same thing as a function of memory moved across DRAM, we find that the snap potential is comfortably in the compute bound region. So if we break this performance down of the snap potential using a proxy app, which is the test snap, we look at snap consists of 4 different algorithms. And you see that between the 4 of them, the compute Y is the most arithmetic intensive. And using the same, now that we understand the performance of the constitutive parts of testnap on V100, what happens if we run the same code with no modifications, no changes, and using pretty much the same compiler, but of a different on a different vendor's GPU? We find that the arithmetic intensity is slightly higher and the performance is also slightly higher. And this is because there might be better memory protocol using the same compiler on this machine. And this is a good feedback that the potential developers can now give back to the compiler designers, saying that, hey, we get a better performance for the same code on one GPU from a different vendor. And these kind of feedbacks are important when it comes to the robustness of the system and running MD simulations efficiently. And so just to give you a conclusion, roofline analysis can provide a true measure of computational efficiency of MD potentials, which is independent of the problem size and type. And the analysis, the beauty of it is it can be performed without intrusive code changes, and it has to be performed once for every change in the algorithm. So if you do not change the algorithm, you have a roofline analysis that you can provide and give it as a proof of efficiency. For users, this is important because now you can choose your MD potential based on the accuracy, the speed, and the efficiency, not just based on the accuracy and speed. And rooflines can be especially helpful when requesting resource allocations, let's say to NSF or Exceed, in the form of proposals. You can include them along with strong and weak scaling. For the developers, now you have a true measure of performance portability, and any future modifications now can be baselined using the roofline analysis to show how efficient was your base algorithm. With that, I would like to thank Dr. Rahul Gayatri, Aidan Thompson, Danny Perez for their incredible help in this work. With that, I thank you for attending my talk.